I learned a new trick that I can mute the picture so that I don't get blinded by the projector. So that was a bit better. So we only had one slide left in the last lecture, but we were about to go overtime, so I saved it for today. And basically what we're going to look at is a pressure test of a hose. So they're basically going to put so much pressure into the hose that it bursts. So it's just to give a certain feeling of what's going to happen. So they're going up to 1,700 bars, so it's quite a lot of pressure. So with 1,700 bars, you get some insane forces once stuff like that bursts. As you can see from the picture there, the hole itself isn't actually all that big. And then you just get a huge explosion coming on there. And this is the manufacturer of those hoses, and they use them a lot on excavators and stuff like that. So that's the same kind of hose, which burst at 1,700 bars. So I can't remember what they were approved for, but I think it was 1,000 bars or something, 700-800 bars for the hoses. That's the pressure they were approved for. No, it's rated for 420 bars actually, and it could hold 1,700. So it just shows that usually they have some insane safety factors on stuff like this. But it is also, you saw the force that comes with this explosion once it bursts. You really don't want that happening in a work situation. Let's see here. So in the last lecture, we looked at how the hoses are built up. We became familiar with different kinds of accessories also. And we learned to calculate the cross-section of hoses and pipes in order to avoid having too large of a differential pressure across a certain length of pipe or hose. We know how the structure of a hydraulic hose is usually built up, where we have an inner tube, we have some strengthening layers, and then we have an outer tube. And this middle part with the strengthening steel mesh can usually be, in some cases, it can be both 2, 3, and 4 layers thick. It just depends on how much pressure you're supposed to have inside this hose. And we looked a little bit at how hoses are supposed to be mounted so that you avoid accidents happening with overstraining your hoses. And we became familiar with different fittings and couplings for the hoses that we had them. There was quite a lot of pictures and stuff on this one, so we had a lot of references to put in. And then we'll start with this week's lecture. So we're going to become familiar with piping. So we looked at hoses in last lecture. Now we're going to look at piping. And we're going to look at the connectors used on pipes. And we're going to become familiar with connecting plates and look what that is. So that's a different way of connecting valves together in a system. And we're going to get to know how an exhaust valve works. Earlier we've looked at bleed-off screws in order to get air and trapped air inside our system out of the system. But now we're going to see how we can use a valve that is going to open up and release the trapped air and then close off so that none of the oil escapes. Then we're going to become familiar with pressure gauges and how they work. And we're going to get to know how a Bourdon tube pressure gauge works. That's the one that's the most in use. And we're going to become familiar with different kinds of flow meters to measure the flow rate that we have in a system. So we'll start off by looking at piping. And it's usually seamless precision steel pipes. So that means that they're thin enough to be created as one hole. So there's not a seam going along the length of the pipe. If you have too large of a diameter of the pipe, you have to start off with a steel plate, and you have to roll it into a cylinder, and then you have to weld it together, and then you get a seam going along the length of the pipe. But for pressure, when you're going to put pressure through it like this, you really don't want a seam going through it. So as long as you can avoid it, you try to avoid it. Of course, with flow lines and stuff for oil production, you often have to have really huge dimensions, and then it can be difficult to get a hold of seamless pipes for it. But at least for hydraulics, you want seamless precision steel pipes, and they are in the European norm 10,305. So that's the standard which says how these pipes are going to be produced. And we need to know about the wall thickness of the pipe, because it's going to be a function of the maximum pressure inside the pipe, and of course the safety factor that we need in case we get switching impacts, so that if we have a valve that switches very quickly, we can get these shocks going through our system when we switch between one position and another in our valve, or possibly pressure peaks from external loads that create pressure peaks in our system. So we have to make sure that the wall thickness of our pipe is strong enough to still contain the hydraulic fluid, even though we get pressures above our operating pressure there. So that's one of the important things to think about when we are calculating it. And the basic way of calculating it, it's not a part of the book there, but you can find it in mostly any technical formula compendium or something like that. It's if you have a tube, the cross-section of the tube, and you have internal pressure. So all the way around you have pressure pushing on it. It's going to try to basically rip the wall apart. So by putting pressure on the inside, it's going to sort of force the outside of the pipe more and more apart. So it's going to try to rip it open. And the calculations are pretty easy. You find them in quite a lot of formula. I haven't checked, but I'm 100% sure that you have the formula in the Metal Trades Handbook, the small blue one that you've gotten. So it's very easy to figure out of, and it's a straightforward formula. So you put in the pressure you have and the diameters and wall thickness you have and stuff like that. So it's really easy to calculate it. And when we're using pipes, we can bend them, and then we can, depending a bit on the wall thickness of the pipe and the overall diameter of the pipe, we have to choose if we want to heat them up first or if we're going to bend them while they're cold. And then we have to use appropriate tools to bend them, because those tools will maintain the circular cross-section within the pipe. So if you just put them towards your knee and start bending it, you're going to distort the cross-section, so it's going to be oval instead of circular. But with the bending fixtures in place, it's going to sort of strengthen the sides so that it's going to keep it circular all the way around, even though it's bending it. And here we get a short clip of how they bend pipes. So this is a fairly thick pipe, but it's the same principle for smaller pipes.
Pro Tools hydraulic Deluxe bender kit. This bender is set up with an air over hydraulic pump, but we also have a 110 volt electric pump that is a little bit faster.
So he's locked the end of the pipe in place there, and he's keeping it straight over here. And we can read off the amount of degrees that he's bending it right now. And you can see that it's kept in place inside two half cylindrical faces there, so it's sort of maintaining the circular cross-section all the way around. So if he wants to continue bending it further, he has to change the grip of it, because the piston doesn't reach all that far. So it's an easy way of getting more from the system. Now it's up to closing on 70 degrees here. And you can see there it was almost at 70, and once he let off the pressure, it sort of jumped a little bit back. And that's the internal strain of the pipe just pulling it back there. So it was within the flexible range of what it could be bent. So within the yield strength of the pipe, basically. So the important part when they're bending stuff like this is to have the correct radius of all the fittings here, so that it fits the type of pipe that they're bending. So after a pipe has been bent, it must be rinsed if it was bent in a cold state, so that if it was room temperature while they were bending it. So they have to rinse it out, because you're going to get flakes of the material sort of popping off on the inside, so that you need to get that out of the pipe before you start using it. Or if it was hot, it's going to have been hot enough to establish a layer of scale on the inside of the pipe and also on the outside because of the heating process. And then you have to get that removed before you put them into use. So then you have special equipment that you put into the pipe and sort of brush it out, basically. And you can have suitable connections, whether you're connecting two pipes together in order to continue on one line, or if you are connecting the pipe directly to a component. So for pipe fittings, they usually have a nominal diameter of less than 38 millimeters, but it depends a bit on the operating pressure that they have. And flange joints is what's used if you have a nominal diameter that is larger than 30 millimeters. So a fitting, if it's fairly small diameter, and then you go over to using flanges if it's starting to get fairly large. So 30 millimeters, it's not that much, 3 centimeters, but it's large in when you're comparing it to a hydraulic system. That's a large diameter. So in a processing plant, you usually see pipes that have this sort of diameter, and then they're going to have flanges either no matter what, because they're too large and they're going to have large pressures moving through them. So a pipe fitting can be made in several ways. One of them is with a cutting ring. And we have a DIN, so that's a German standard. So 3850, which sort of sets up what pipe fitting is what. And you have the solder-free pipe fittings. You have cutting ring connectors, which is the one that's shown down here. Did I lose my pointer? So the one that's shown down here is the cutting ring connector, and we're going to look closer in on how that one works in the next slide, because it has a very common use. It's very often in use. You have double bevel ring connectors. You have soldered and welded pipe joints. So soldering is when you're basically when you're melting a metal and letting it float into cracks. That's when you're soldering. And when you're welding, you're melting a metal along with the material that you're welding together. So then you're fusing it together by melting all of it. But with the soldering, you're only melting the metal that you are actually adding. You're not melting the base material of the pipe. So soldering is used in smaller connections. Soldering is also what they use quite a lot of in electronics when they are connecting wires. So they're using small soldering apparatuses then. And you have the flanged bushing connectors also, when you need the flanges. And you have ball-type nipple connectors. And as I mentioned, it's the cutting ring connectors that are most commonly used. I think I have to change the batteries on this one. The laser is starting to dim on me here. So this is a cutting ring connector, where we have the one marked number 1 here. That's the male part of the connector. Number 2 is the nut, which you will basically tread into or onto the pipe before you start installing everything. So the nut part has to be put onto the pipe beforehand. Then you put the cutting ring in place, so that's the red one over there. So you put that one also in place, and then you can come in with the male connector and put to the end of the pipe. And number 4 here is, of course, the pipe. So when you then trap the cutting ring between the nut and the male part of the connector, you then start to screw the nut onto the threads of the connector. And as you continue screwing, you're going to push the cutting ring, and it's going to basically cut into the pipe in 2 locations. So it's going to cut in over here, and it's also going to cut in over there. It's a bit difficult to see there, but you have 2 locations where it's cutting into it. And this is around the entire circumference of the pipe. So it's going to create a tight seal there, so that you won't have, you don't have need for putting an O-ring in here or anything like that, because it's going to be completely tight, because it's metal forced into metal, and it's all the way around. So it has no way of releasing anything there. So that's the way the cutting rings work. And of course, if you're going to change the connector on a pipe, you're going to have to decide if can you allow it to be deformed there by the cutting ring, or do you have to actually change the pipe also? Do you have to cut a small part of the pipe or something like that? So you have to be a bit aware that it might not always be really reusable, all of this, when you've used it. So I think I'm going to start using this one until we have a break, and I can go get a battery. So with the DIN designations for cutting rings, we have 3816, 3862 for double bevel ring. We have a different one for ball lining, a different one for flange bushings, and a different one for pressure rings. So it's all of them have their own standards of how they are going to be set up. And often the standards are also giving the nominal sizes of these connectors, so that you can go into the standard and you can see that, well, you can get one of this size and one of that size, but there's nothing in between, so that you have to fit them up to the pipe dimensions that you are intending to use. So if we're using a union nut to put them together, so the nut part of the connector, we can have a cutting ring, double bevel ring, which is a similar principle, and we can also have soldered or welded flanges on the pipe end, and using union nuts from that DIN standard. And from the 3872 DIN standard, we can use a cutting ring with a pressure ring. And then for union screw, we also have cutting ring, double bevel ring, ball lining, and flange bushing. So this is sort of, the book is going extremely into detail on these different parts. Mainly when you're going to design a system, you are probably working with a supplier. So you are most often just plucking what you need from their catalog. So it's maybe they even have some consultants which you will talk with, and they might say, well, if you use a 3870 with a cutting ring, that's going to be the best for your design, this one. Then, of course, you will listen to the consultant who's working for your supplier, because he knows what he's talking about, hopefully. You can't be 100% sure, but he should know what he's talking about to have a job like that. So. Then we have other pipe connections. So we can have a straight connection where we're just continuing on the same line. We can have bulkheads, welded and soldered connections. So basically welding it together using heat to connecting pipes. We can have them at an angle, an L connection, a T connection, cross sections, so that they are basically an X when we are done with them, a 90-degree angle. You have a different DIN standard for that one, so it's sort of a jungle of standards out there when you start looking at stuff like this. And for larger pipes, we use flange joints, because usually for larger pipes we get higher pressures, and as we saw from the connection on the connectors, if you got a large enough diameter, you went over to a flanged connector to put on it. But if you have a really large pipe, you're going to have a flange that is welded to the pipe end. So it's not screwed in place with a connector, it's welded to the pipe. And the commonly used thread types you're going to see when you're working with piping. You will have the Whitworth thread type and precision metric threads and NPT threads, so they're tapered. When we've been working in CAD now, for both Group A and Group B, we've been creating threads yesterday and today. So then we were working with metric threads, and we were actually working with fine pitch on our threads, but we weren't working with precision metric threads. So they're slightly different. So it's a different standard they're following. It's not the regular ISO metric threads. I think in Inventor that it's called isometric pipe thread. I think that's what they're called in Inventor. I'm not going to say that for 100% for sure, but it's not called precision metric threads, at least. I'm not sure how far you've gotten with Torbjørn on bolts and threads and fasteners. Have you looked at the profile of the threads, seen what the angle is and everything? Then he's probably going to do that next week with you. I know he's been preparing lectures for that. At least I've seen it on a screen. So it's fairly soon that you're going to have that. Let's see, that was a bad marker. So if we cut along the length of a bolt so that we can look at the thread itself, we're going to see that it's basically shaped out of triangles. So we could extend this and get sharp points. The only reason why there isn't sharp points on the threads is basically being able to cut a sharp point into the material. That's very difficult. So it's easier to have a flat section at the end there when you're cutting it. And of course, if we had sharp points on the tips of the threads, we were going to cut our fingers whenever we were handling this with our hands. So we want them to be flat on the tops there, so that they're not going to be sharp. For the metric threads, we have an angle of 60 degrees between them, so that we know that when we have metric threads, there will always be 60 degrees. The same is if we have what's it called? Unified threads is the name for it, but in other words, instead of being measured in millimeters, they're measured in inches. So that's basically most of the difference. So they have inches instead, but they're still using the 60 millimeters. So if you match up the correct correct bolt in inches, you can use a nut in millimeters, and it's going to fit, so long as you find the correct match with the diameters, because they have the same angle between the threads. Now for Whitworth, it actually uses 55 degrees. So you can't put a Whitworth nut on a metric bolt. It's not going to fit. You won't get anywhere with it. But with using the 55 degrees, it allows the Whitworth profile to be sort of more shallow, so it doesn't have that much height there, and that's a positive thing when you're putting it on a pipe, because the pipe is hollow, so you don't have all that much material to start cutting your threads into, and that's also why we are using precision metric threads, because they also have a very much more shallow profile, so that they won't cut that far into the material. They will still have quite a lot of strength, but they won't cut that far in. And then you have different kinds of thread types that use tapered heads. You can also get that with metric threads, that they are tapered, which basically means that the threads will start off, and you can sort of get an angled line going through them, so that as you are screwing something on here, the diameter is going to start increasing and increasing as you screw the nut on, so that it's going to become more and more tight as you get to the end, and then it's going to be completely locked in place, so that you won't get any fluid escaping through the threads there, because it's going to basically metal against metal when you've put it all the way in. And that is one other way of, by using a tapered head, you can avoid having to use an O-ring or some other sealing surface in order to get the tight seal for that connection. Then we're going to start looking at connecting plates. And they are directly connecting our valves together, so that you don't have to use a hose or a pipe between each individual valve. And that means that we don't need that much hoses and pipes in our system. It becomes more compact, and it is also going to cost less. Preferably. It depends a bit on the size of the connecting plates and how much hose and pipe you are managing to get rid of by using the connecting plate, of course. If you're getting rid of 10 centimeters of pipe, and that's all you're getting rid of using the connecting plate is most likely going to be more expensive than using that 10 centimeter pipe bit. But if you're connecting 4, 5, 6, 7 valves together, then it's better using connecting plates, because then you have quite a lot of sections of hose or valve, hose or pipe that you don't need to use. So overall effect is going to be more cost effective, and of course you're going to get more reliability in your system, because you don't have that many connections between them. You have if you use a connecting plate, you have a direct path from one valve to another. If you're using hoses or pipes, you're going to have one component, one valve. You're going to have a connector, then you're going to have a hose, then you're going to have a connector, then you're going to have the other valve. Then you suddenly have quite a lot of places where you could get a leak. So potentially you have more risk of something going wrong in your system. And connecting plates are very commonly used, especially where you need compact systems. So we've talked a bit about it before with these manifold types in placing many valves in one manifold. Like in ROVs and stuff like that, you want to get it really compact because you don't want to take up too much space. And it also allows for very quick valve replacements because you have instant access to all of your valves, and you don't need to start disconnecting lots of hoses and all of that. You just need to unscrew your valve. Of course, make sure that you have depressurized the system. You don't want to have the valve popping out. And you also get shorter flow paths for your hydraulic fluid, so that you're going to have less length of flow paths that the hydraulic fluid needs to pass through, so less volume that you need to have in your system, and also less differential pressure loss across the lengths. So it's very positive in that regard. They're usually following the ISO 4401 standard. And just like we looked at valves themselves, where they can have standardized ports, where you can just put the flat of the valve onto another component or whatever it is that has the same port setup. You can just screw it into place and you're going to have a direct connection. It's the same for these connecting plates. And different places where they're used is to connect valves that are parallel to each other in a manifold. So they are all on a line and you are just connecting them up on that line. You can have special control blocks that you can actually stack. Either you can stack them horizontally or vertically if you want to. So you can put several control blocks together. And then you get minimal piping expenses when you do that, because you don't need to have pipes between each of them, as we've already looked at. And it's a typical image of how a connecting plate or control block is going to look like. In this case, we have the possibility of putting a valve in there. So the valve can be screwed in there. We have holes going through it in order to be able to mount it to something else. So those are just clear holes going all the way through, which you can put a bolt through and screw it on tightly. And then we have ports for, there's probably a port on the other side also to connect other valves to. So I found this picture. It's from a so-called, they call them webinars, where they actually do sort of a mini lecture answering questions and stuff like that on video. So a couple of representatives from Sun Hydraulics did a webinar about their cavity advantage, as they call it. So the openings that we screw the valves into are called cavities. So they had one there. I've got it linked in the references. This is just a screenshot of the first image on that video snippet. I just liked it very much because it showed this cutout of how they look. So one thing that you can do in this one, for example, you can connect a hydraulic line in here, another hydraulic line in there, and this is a valve going in so that we have the different valve functions built into this part. And there is a control section. You can see there is a knob that can be turned around there to control it. You have the possibility of connecting another valve in here also. Or if you don't need that other valve, you can just block it off with a bolt so that it's tight. And what you can do with blocks like this is that you can set them up one after the other, and then you will have connections between them, so that you don't need to run a short length of pipe between them. You can just put them together and have a sealing between them there. So you just have an O-ring sealing or something between them, and then you get the full seal as you put them up. So if anyone is interested in seeing that one, they can find the link for it in the references of this presentation. We'll do a break before we continue. Right, on the following diagram that we have here, we've basically put up the functions of 3 valves. So we have the pump down here. It's delivering pressure into a line. It's going to a pressure reducing valve, a pressure relief valve, in order to handle if we get any pressure peaks or anything like that. We don't want to have too high of a pressure. We also have a different valve, which is solenoid actuated, which releases fluid back to tank, which means that we are allowed to activate this one if we just want to circulate the fluid from pump and back to tank. For an example, if we are going to close this one off, whatever we're doing up here means that there will be full pressure in the system, that the pump will basically just be pushing against the wall. So most likely there is a double acting cylinder connected up here, and if you push the cylinder all the way out, then the pump is going to start to just pushing against the end of the cylinder, and it's not getting anywhere. And if this is a situation that you're going to have for quite some while, you would want to activate this one so that you would allow pressure to move back into the tank. So especially if it's like going to be, you know that it's going to be half an hour before you can start running the cylinder again. It's nice to have an option of recirculating it. So what's been done here is that instead of putting hoses or pipes between all of these to connect them, they've used connecting plates instead. So it's typical. So we have some sort of connecting plate, not specifically that one, but some sort of connecting plate. Along with the pressure relief valve that's in the bottom, closest to our pressure line. And we have pressure coming in here into the plate, and it has a direct pathway into the pressure relief valve, which also, when it opens up, creates a direct pathway back to tank. So we have that possibility there. Also, if we had need for any pilot pressure or anything like that, this particular connecting plate has ports going all the way through them for that reason. So, but this valve isn't using any pilot pressure other than what it's getting at the input port, so it doesn't really need to have anything connected to the X or Y. Then we go to the next connecting plate, which is stacked on top of this other one, or beside it, or however they've put it up. In this case, it looks like it's on top of, since they've placed it on top. And again, we have the pressure coming from the pump. It's moving into through the first connecting plate into the second connecting plate, where it has a direct pathway to this valve, which, when activated, creates an opening back to the tank, going through the first connecting plate there. And then the same happens for the next one. And this one, you can see it actually blocks off, so this one doesn't have the X and Y ports, so it just comes to a stop there. They weren't necessary in this case. But we have the pressure going through the first 2 blocks and then up to the 3rd block, where it goes over to the valve, and it can either be sent to the B port, or if it's shifted over, it can go straight up to the A port. And of course, we have a return to tank and through the first 2 blocks there. And then we have the pressure gauge, just so that we can keep an eye on what the pressure in our system is, which is placed on a 4th block all the way up top. And the pressure is going through all the 3 first blocks and up to the 4th one and into the pressure gauge, so that we can read off the pressure in our system. And this just means that you have 4 blocks similar to this one, which are lying on top of each other, and that's all you need, instead of having one valve and some hoses going through, like we have in the lab. We have hoses going between everything. So here instead you have everything neatly stacked in a small, compact block, basically. So this is the way they use connecting plates to design systems. So again, when we have full pressure, it goes through all of the blocks and into all of the valves, just like it would have done here with full pressure. And then our return pressure also goes through all of the valves and back to tank, just like it would for each individual one. But for each individual one, we would have had to have a separate hose going back to the tank, or connecting them, all of the hoses together and then going back to tank. So you save quite a lot of space with this stuff. So you can use vertical stacking for the connecting plates, and then you use adapter plates with valves in and connect them together in a vertical stack when you're setting it up. And you screw all of these to a common plate so that all of them are connected to the same plate, so they can't really move or anything like that. Then you have horizontal stacking, where you line up one after the other for systems that have several control chains. And the individual valves, or even vertical stacks. So in a horizontal stack, you can actually do horizontal stacking of vertical stacks. So you can set several vertical stacks in a horizontal stack. So it's, you can have quite complex systems when you start putting all of this together. And then the third option, which is cartridges, which is more what Sun Hydraulics do, which is even more specialized. And then you can do various switching functions by individually activating two-way valves. And they're in the cartridges, so that you get one block might have several two-way valves in order to achieve what it's going to do, and then you're going to individually activate them in order to get the correct effect from it. It depends a bit on how the system is set up. But the cartridges they're difficult to get economical if you have a small system. So you need many of them. So you need to buy them in quantities when you are buying them in, and you usually need to have quite some size to your system in order to make this work financially with regards to just using regular stacking for the others. Then we're on to exhaust valves. And just like the bleed screws, if we're using bleed screws in our systems, we want them to be placed at the highest point in the system, because we need all of the air is, of course, lighter, has less density than the hydraulic fluid, so it's going to rise to the top no matter what. So by putting in the exhaust valve in the highest point in our system, it's definitely going to be wherever there is trapped air. And instead of having a bleed screw that we have to go and manually check every now and then if we can release some air from it, we can have automatic exhaust valves. And this is how the automatic exhaust valve works. So we have a pump and a directional valve running a double-acting cylinder in this case. And most likely, the cylinder is tilted or something so that this end of the cylinder is the highest point. So that's where all of the air bubbles are going to accumulate over time. And that is also where we have the exhaust valve, so the valve up here. So right now, the piston is all the way back. We have fully retracted the cylinder. But once we put some pressure into our system and we start advancing the cylinder, we are going to increase the pressure on the piston rod side of the piston rod chamber, which means that we are going to have some pressure pushing against the valve up here. And since there was air trapped by the valve, so in front of the poppet part of the valve there was air trapped, it's going to start increasing its pressure enough to push the valve open, which means that the air and a little bit of hydraulic fluid can escape past the seat of the valve, which was keeping it completely sealed. And the air can escape along the sides of the puppet and out into free air, so that we get it completely out of our system. Oops. So the air escapes past the piston and out of our system. And when all the air has escaped, the puppet here is going to be hit with the full pressure of our hydraulic fluid, because up until now it has mostly been hit by the pressure of the compressed gas, which was escaping past it also, so that it was basically just a flow of gas, the amount of air that needed to flow past the piston that was in direct contact with the piston there. But as soon as all of the air has escaped, it's going to be only hydraulic fluid that hits the puppet there, and it's going to push it all the way to the end, and then it's going to seal off at the top there. So none of the hydraulic fluid manages to escape past the puppet and into free air. So it's going to be completely sealed by the pressure in the system. And this is when we have the cylinder completely extended. So if we start retracting our cylinder, we are going to put pressure from our pump into the piston rod chamber, which is going to keep pressure on that puppet, so it's going to keep it closed. But then as we move the cylinder back and forth, we might get some more air into our system. Maybe we've pulled some air in through our tank and then through our pump, maybe just a couple of bubbles or something like that. But over time, it's going to start accumulating and start becoming a pocket of gas inside the chamber here. And then we're going to have the same effect all over again, that the gas is going to sort of relieve the pressure a little bit here, so that we're going to get the ability of releasing the gas before the hydraulic fluid closes the puppet valve again. So it's a really simple design to get rid of what is potentially a servicing problem, where the alternative is to have someone come in and manually open a bleed screw and get the air out every now and then. But now it's going to automatically do it whenever there is enough air in the system to be a problem. It's going to open up and release it. So it's never going to be subjected to a problem with a technician forgetting to do a routine. So if it was a bleed screw and it was supposed to be opened once a month to let it out, what if the technician responsible for it was off sick or something? Maybe he had broken a foot off for 6 weeks on crutches, and no one else remembered to open the bleed screw. And suddenly you have gone for 2 months without getting air out of the system, and you might have too much trapped air in the system, so that it's going to affect the function of the system. But having an automatic valve is going to help you do this more reliably when you have it. So then we're going to start looking at pressure gauges. So we have pressure gauges and flow meters, the last two things on the curriculum, and then next week we are going to start working with different systems and doing some calculations with them while we're working on them. But the first one we're going to look at here of the pressure gauges is the Bourdon tube measuring unit. And it is the most common one, which is also why we need to know how it works. The other ones we just need to be familiar with, that they operate in different ways, but the Bourdon tube is nice to get to actually know why it works the way it does. And it's using a bent Bourdon tube, which is C-shaped, and that's the red part here that's going behind the dial there and then over here. And inside, if we had cut this in two, the C shape, and looked at the cross-section inside, it's going to be an oval. So it's not a circular cross-section, it's an oval cross-section. And then it's connected down here and into the pressure system. And when we get pressure into the system here, it's going to affect this tube. So that it's going to create strain from inside the tube. When we get pressure inside the tube, it's going to start straining against the material. But since it's oval in cross-section and then bent in a C shape, it's going to exert a greater amount of force on the outer edge of the C, meaning that since it's see, if we have the C tube here, it's going to put more pressure on this side of the C tube. And basically more pressure means that it's going to try to straighten out that side of the tube. So it's going to push it, which means that this end of the tube will start to lift up just by increasing the pressure in the system. So you get an increased pressure inside the tube, and that's going to try to straighten out that C shape. And that's why it's connected over here to some mechanisms, some levers, and they pull on the dial here, and it's going to show the amount of pressure that you have in your system. So a Bourdon tube like this has a certain pressure range, so that if you go past the pressure range, you are going to destroy the mechanism in there. So if you have a pressure gauge that is up to 80 bars, and you run it on a system with 150 bars, you're going to break it, and then it's not going to work afterwards. So you're going to have to get a new pressure gauge for it. So yeah, the tube tries to straighten out, and through all of these levers, we are transferring the motion to the dial and showing it with the pointer on the dial, exactly how much it's going to be. And then we can read the pressure from the scale on the dial. And one thing that I know, if a Bourdon tube pressure gauge has been subjected to too much pressure, so it's been destroyed, it might not actually be visible to you. So you can't actually see that it's going to show you the incorrect amount of pressure, because it might spin several circles around there before you sort of get a reading on it, and then when it pops back down again, it might just look like it's not slightly out of calibration, that it doesn't quite hit zero when it's supposed to hit zero. So maybe you adjust it so that it's going to show zero, and then when you start using it, it's going to be way off with the amount of pressure it shows. So it's often important to know if it might have been damaged, and then to check it if it's showing the correct pressure. Yeah, with both if you have too high pressure in your system, or if you get a significantly large enough pressure peak in your system, it's going to break the pointer of it. So we have a very nice clip of a guy that's dismantled a pressure gauge like this, and he gets to show us how it works.
Hi, and welcome to another episode of the Kodiak Classroom. In this episode, we're going to go over the internals of a pressure gauge, as well as briefly go over how a pressure gauge works. Now, for simplicity reasons, I'm going to be doing this on a 4.5-inch dial gauge, but 1.5, 2-inch, 2.5-inch dial gauges all have the same type of internal construction. And I'll show you a smaller gauge towards the end of this as well, but obviously for video purposes, it's easier doing on a bigger dial. So what are the parts? Well, first we're going to look at the socket connection. Okay, the socket and the connection are all one big piece of metal that's hollowed out, is where your orifice is that connects to the media. The socket is then welded to the second part, which is the Bourdon tube. The Bourdon tube is this C-shaped metal you see. Now this gauge is calibrated for a 60 psi. The Bourdon tube metal and construction is designed specifically for the range. So for instance, on a 5,000 psi gauge, you might see a little bit of a thicker Bourdon tube, but ultimately the design is the same. The Bourdon tube and the socket are the only two pieces that will actually touch the media. So those are the pieces that are going to be made of brass, stainless steel, Monel or steel in some cases, all depending on how corrosive the media is or what you're trying to do. The most common being brass and stainless steel. Now the end of the Bourdon tube is connected to a link here. That link is then connected to a sector, which is a half circle gear. And I'll bring this a little bit closer to show you. I'm grinding it here. That's the gear. The sector is connected to a gear on an axis, which is hard to show in this video, just due to some of the pieces here, but that's connected to an axis, which is then connected to the pointer on the other side. So the idea behind a gauge has been around since the mid-1800s. What happens is as the media enters the orifice and then goes through the Bourdon tube, which is hollow, the pressure wants to make the Bourdon tube straighten out. That's connected to the link, which then moves the sector, which moves the gear, which moves the pointer. So as I move the Bourdon tube, you can see the link moving and the sector gear towards below my finger kind of going back and forth. That's moving the needle on the other side, which I'll show you here. And that's really all there is to it. Now, when picking a pressure gauge, it's important to know what your application is. So the other side is that there's obviously a lot of pieces on the inside of the gauge, which can be susceptible to vibration or pulsation in the line. So it's important to use liquid filling or snubbers or pulsation dampening movements on the inside, because what can happen is on a vibrating application, you get a lot of back and forth movement, okay, which is grinding the gears and moving the needle frequently back and forth. This ultimately will damage the gauge over time a lot quicker than normal usage. The other thing is pulsations. Pulsations are anything really a fast pressure exceeding the range of the gauge. So for instance, this is a 60 psi gauge, and if we had an application where, you know, all of a sudden you open up a valve and 300 psi hits the gauge, what's going to happen is it's going to exceed what the Bourdon tube is made for, and it's going to try to straighten it out. And if you exceed that, the Bourdon tube may not go back to its original C shape as far as it was before. So what can happen is you'll see often a gauge stuck here when there's really 0 psi in the line. So these are all things that can be prevented with, as I mentioned before, liquid filling, pulsation dampening, snubbers, things like that. For a real quick show, I'll show you the 2.5-inch dial, or this is actually a 2-inch dial. And just to show you, it's the same amount of parts, just a lot smaller, which makes these a little bit more sensitive to some of your more rugged, bigger dial gauges. And you still have your socket here, Bourdon tube, your sector, and then the gear connected to the pointer on the other end. So as I move the Bourdon tube, the pointer moves. And that's really all there is to it. If you have any questions, please feel free to email us at kodiak@kodiakcontrols.com or visit us at kodiakcontrols.com. Thanks, we'll see you next time.
So as he mentioned, having them liquid filled in order to avoid getting too much vibrations in them. And those are the ones we looked at all the way at the beginning of the first lecture, where they were filled with a glycol, this gel-like substance. And what that does is that once the Bourdon tube starts moving from the pressure, it's going to have some resistance from the fluid, because it has to push against the glycol that's inside the pressure gauge. And this means that it won't be able to move as fast. So instead of vibrating very quickly back and forth, it's going to move more slowly back and forth, because it has to push against this glycol, which, as he said, it makes it last a lot longer, because you don't have that much wear and tear on it. And you can see all of the parts in there that were quite a lot of metal parts in there. So in the case of using a regular gauge like that, subsea, where I talked about filling it all the way up with glycol, so avoiding having those air bubbles inside it, or for an example, cleaning it completely out and letting it fill up by seawater rather than that. So basically letting the seawater do the job of the glycol in there with the dampening effect. Was going to save the pressure gauge from being broken by the pressure, the external pressure of the water. But letting it fill up with seawater means that you have a lot of metallic parts in there. You have seawater, and it's going to be quite impossible to clean that off completely afterwards. So you're going to have a lot of corrosion happening inside your pressure gauge. So for one-time use or a couple of time uses, fair enough, but you're going to have to very often switch out those pressure gauges if you use a quick solution like that one, instead of using a more expensive pressure gauge that has been built for subsea use. There are other types of pressure gauges also, which use a capsule or a diaphragm. So we already remember the diaphragms from that we looked at with the accumulators, where we had diaphragm accumulators. It's sort of the same principle with the diaphragm pressure gauges, because we get increased pressure inside the capsule or behind the diaphragm, and it is going to make them bulge. So either the capsule is going to bulge outwards, or the diaphragm is going to bulge in one direction, in the opposite direction of the hydraulic fluid then. And then we have some measuring tools that measures this bulge, and it transmits this information to the pointer on the dial. And usually this is a mechanical transfer of the information. So we have something that's lying against the capsule or the bulge, and when lying against the capsule or the diaphragm, and when it starts to bulge, it's going to move this mechanically, and that's going to transfer it, just like with the Bourdon tube, it's going to transfer it to a pointer on the dial. And they usually don't have very large pressure ranges. They can handle fairly high pressures, but they can only handle a certain range, so then you are locked to having, if you have an operating pressure of 150 bars, you can never have less than 125 bars, because it's not going to handle a larger range than that. It can just show you from 125 to 150. So it's not going to be able to show you if you get 80 bars in your system pressure. It's still going to show 125. It's not going to show you exactly how small of a pressure you have. So they're a bit, I imagine that's one of the reasons why they are less in use than the Bourdon tubes. The Bourdon tubes usually have a higher range that they can show. Then we have the piston type, which is basically what it sounds like, where we have hydraulic fluid pushing against a piston. And the piston has a compression spring on the other end, which will put it back if we lose pressure in the system. And what happens is that the pointer is directly linked to the piston itself. So as the piston moves back and forth, it's going to move the pointer back and forth. And then the pointer indicates what the pressure is on a dial, as with all of the others. But the nice part with a piston one is that it's not going to be damaged by high pressures, because the piston is going to move against the compression spring until there is nowhere else to go, until it stops at the end, and then it's just going to stay there. It's not going to be deformed or anything like that. It's just going to stay there. So it's going to show a maximum amount of pressure, and you probably have a lot more pressure than that, but it's just going to stay there. It's not destroyed for afterwards. It's going to just pop back to the correct position. So if you have a system that is going to be subjected to quite a lot of high pressures or pressure peaks that are going to be a bit uncontrolled, you don't quite know when or how they're going to happen, then I would choose a piston pressure gauge, just to be on the safe side, because then you would have a pressure gauge that was going to work no matter what had happened in the system. So it's just going to continue to work. Then you also have pressure sensors, which are electrical. So usually you have a quartz type pressure transducer that reads off the pressure, and that uses the piezoelectric effect, which is very, very, very small amounts of current and voltage. So it's really, really tiny when you start looking at it compared to other electrical systems. And then again, we are using a diaphragm where the pressure acts upon the diaphragm. And the diaphragm is moving, or the diaphragm is bulging, it's moving this quartz transducer, which is going to generate a voltage and current. And this is going to become an electric signal, and it's going to be amplified. And then it's being transmitted over to wherever you're getting it shown. So whether it's a computer that receives the signal and shows it on a screen, or if it's an electric pressure gauge that shows it directly on the pressure gauge, that might also be. But they are usually capable of showing very small changes in pressure. So they are very, very good at getting accurate readings of pressure. Then you have strain gauges, and those are attached to a diaphragm. And as the diaphragm bulges from the pressure, it is of course being strained, so it's being stretched by the pressure. And then the strain gauge will read off how much strain there is on the diaphragm, and it's going to convert that into an electric signal and sending it to the indicator, which will usually have an amplifier built into it, so that it will receive a very weak signal, but then it will amplify it and use it to show, indicate the pressure. And so with the quartz one, the amplifier is usually inside the pressure sensor, while with the strain gauges, it's often at the receiving end instead. The nice part with pressure sensors is, of course, that you can have them at remote locations. So that is what's being used subsea and parts like that, where you can have a way far off compared to where your control room is, and you're going to get to see what kind of pressure you have in the system. And you can also record, of course. You're getting an electrical signal, so it's not going to be a problem to record the kind of pressure you have. So for an example, if you have a hydraulic system where you are getting we're getting strange readings on your pressure, so that you've gotten so far as figuring out that something has to be wrong in my hydraulic system because I'm getting these weird pressure peaks at different times when there shouldn't be any pressure peaks. Then you can record these pressure peaks, and you can try to put them into systems and see what was happening when this pressure peak occurred, so that you can try to figure out why did the pressure peak occur. So it's a good thing to have in order to be able to log everything that happens. And you can also link them directly to solenoid valves, so that if the pressure reaches a certain point, the pressure sensor will actuate the solenoid so that the valve will open or close or whatever it is it's going to do. So you can build up very automatic systems this way. Then we're going to look at volumetric flow meters. And the simple method of figuring out what flow rate you have, if you just need to figure it out for a system one time, just to know what you have in your system, is to use a cylinder and a stopwatch, and basically just time it. How much time does it take to extend the cylinder? And then you calculate what the total volume is going to be once it's completely extended. So then you can divide by the time, and you're going to see the flow rate, volume per second, or volume per minute that you're going to have. So that is one of the possibilities, especially if it's a very simple system that you're going to preset it once to a specific flow rate, and then you're done. It's just going to stay there. And that's the cheapest way of doing it. But then you also have other ways of doing it with flow meters that stay in place in the system, that you actually build them into your system. And then you have the fixed cone measuring tube, where you have flow coming in at one end, going out the other, and it's going to pass along this cone. Then you also have a hollowed out piston here, so it has an opening between the cone and the piston, which basically means that if we move the piston over here, we're going to get a greater cross-section that the flow can pass through. So by measuring off on the scale on the outside here, we can see how much opening we're getting, and then we're going to figure out how much flow we have through it. So this is a very simple system, and it's going to react fairly well to changes in flow rate, and you can read it off manually from it and just see where is the piston located. And usually the dial where it's pointing at has been converted to telling you what the flow rate actually is, so liters per minute. It's been converted to that. Yeah, so the piston is movable, and the hydraulic fluid flows between the cone and piston, as I said. And then the piston is going to move according to the flow rates, giving us a changing orifice or changing cross-section. And usually there is a 4%-ish inaccuracy on these, so that it's going to give you a fair enough estimate of what your flow rate actually is. And if you need more accurate measurements, you're going to have to use a measuring turbine, for an example, where you have a turbine in the center. So you have the flow passing through the flow meter, and it's going to hit the turbine blades and rotating them. And then you have an inductive proximity sensor mounted on it, which is going to get an induction signal every time one of these turbine blades passes, because then you have metal passing close to the induction sensor. And then between the turbine blades, you will have a weaker signal, and then a new blade passes, and you're going to have another one. So then you can read off every time a turbine blade passes the sensor. So long as you know how many turbine blades there are on the turbine, then you know every time it does a full revolution. So then you can read off how many RPMs it has, and that's going to give you the flow rate for it. So you can calculate the flow rate from that. Then you have oval gear meters. So instead of having circular gears, they're actually oval instead. They look pretty weird when you start looking at them, but they work quite fine. So, then you have gear wheel measuring devices, and we can get to look at one here.
Positive displacement flow meters divide a flow stream into fixed, known volumes and count them to determine the total flow and flow rate. In a gear meter, the measurement chamber is created by the gaps formed between precision-engineered gear teeth and the meter's body. As liquid pushes against the gear teeth, the gears progress and isolate a volume of fluid. As liquid continues to enter the meter, the trapped portion of fluid is carried along by the gears until the fluid is released into the downstream side of the meter. This process repeats itself continuously. You will notice the meter is impervious to intermittent or start-stop flows and changes in viscosity. This is unique to positive displacement meters. One benefit to max meters is the high-resolution transmitter that uses a magnetic signal to report the movement of an internal shaft as opposed to counting the gear teeth. In the frequency version of our model G004, for example, this means as many as 500 pulses per cc. Since the external dimensions of the meter are fixed, this creates a repeatable measurement of volume.
So basically it does the same as with the turbine. So it's spinning these gears, and then they're using an inductive proximity sensor to read off the RPMs of these gears. And just like with a hydraulic motor or with a hydraulic pump, we know exactly how much volume there is between each teeth, so that we know for each revolution how much each of the spaces between the teeth are moving around of the fluid. And that's a way that if we get the RPMs, we can just multiply it with the displacement volume, and then we have the flow rate. You can also use orifices to figure out the flow rate, looking at pressure differences, and you can also have baffle plates to figure it out. But those are more at least the baffle plates are fairly uncommon. So for this lecture, we were going to become familiar with piping and different kinds of piping connectors, where we realized that the ring connector is the one that is the most in use. And we looked at connecting plates, and we looked at how exhaust valves work, and the pressure gauges, the Bourdon pressure gauge in particular. And then we became familiar with different kinds of flow meters. So that was all for this week. There's the Sun Hydraulics video, if anyone wants to watch it afterwards, but it was like 20 or 30 minutes, so I couldn't actually play it here, even though it was actually quite informative. So have a good weekend, everyone.